All right, physicist. Tonight you're going to watch a problem done two different ways. First, someone will use all of the UAM equations to figure out a three-part problem. Then I will show you how to solve the same problem by graphing. I would strongly suggest that you get out a piece of paper and you work out the problem both ways.
Number 5. A van travels at a constant speed of 32 meters per second for 5 seconds. It begins to accelerate at a rate of 3 meters per second every second for 7 seconds, and then maintains that speed for another 18 seconds. Finally, it slows down to rest in 22 seconds. How far did the van travel during the course of this entire problem? So there's multiple parts in this problem, and we have to analyze each part separately. So let's start with the first part. The van is moving at a constant speed of 32 meters per second for 5 seconds. What equation should we use anytime an object is moving with constant speed when there's no acceleration? The equation that we need is this one. D is equal to Vt. So V is 32 meters per second and the time is 5 seconds. So notice how the unit seconds cancel. So we just got to multiply 32 times 5. 30 times 5 is 150. 2 times 5 is 10. So the distance for the first part is 160. So I'm going to call it D1. Now what about the second part? It begins to accelerate at a rate of 3 meters per second squared for 7 seconds. Let's focus on that part. So once it begins to accelerate, the speed is going to change. The initial speed is 32. We don't know the final speed. We do have the time is 7 seconds, and we know the acceleration, which is 3. Now, for every part, we need to keep track of the final speed because we may need that for the next successive part. So not only do we need to find the distance that the car travels in each part, but we need to calculate the final speed. So let's find the final speed first. So V final is equal to V initial plus AT. V initial is 32, A is 3, T is 7. 3 times 7 is 21, and 32 plus 21 is 53. So I'm going to call this V2. This is the final speed at the end of part 2. So V2 is 53 meters per second. Now let's calculate the distance that the car travels during part 2. So we can use this equation. D is equal to 1/2 V initial plus V final times T. So V initial during the second part is 32. V final is 53. And T is 7. 32 plus 53, that's 85. Times 7, that's 595. And then divided by 2. So D2 is 297.5 meters. So that's the distance that the van travels during the second part of the problem. Now let's focus on the third part. It says the vehicle maintains that speed for another 18 seconds. The final speed at the end of part 2 is 53 meters per second. So during part 3, the van is going to maintain that speed, or it's going to be moving at a constant speed of 53 meters per second for 18 seconds. So anytime the vehicle is moving at constant speed, we can use this equation. So V is 53 and T is 18. So I'm just going to write this. V3, part 3 is, it didn't change, it's 53 meters per second. 53 times 18, that's 954. So that's the distance that the car travels during part 3. Now what about part 4? Finally, it slows down to rest in 22 seconds. So because the speed is changing, it's decelerating. The acceleration is negative. The initial speed of part 4 is the final speed of part 3, which is still 53 meters per second. Now the van comes to a stop, it comes to rest, so the final speed is 0. The time in this interval is 22 seconds. So we can find the displacement during the 22 seconds using this formula. So V initial is 53, V final is 0, and the time is 22 seconds. Half of 22 is 11, and 11 times 53 is 583. So that's the displacement for the last part of the problem. So to find the entire distance that the van traveled, we need to add up the values that we have. So we got to add up 160 plus 297.5 plus 954 plus 583. So the van traveled 1,994.5 meters. So that's the total distance that it traveled.
This is a different method of doing the same problem. We're going to draw the line on the graph that describes the velocity of the van, and then we're going to find the area underneath that curve, and that area under the curve will tell us our total displacement. But before we can start doing the problem that way, we need to make sure that we know what the final velocity is in the second part of the problem. Otherwise, we can't make an accurate graph. So the van goes for 5 seconds at 32 meters per second. Then it accelerates for 7 seconds. So we need to know after that acceleration, what is the velocity of the van? We are going to use the formula velocity final equals velocity initial plus the acceleration times the change in time. And we're looking for the velocity final when our initial velocity is 32 meters per second, our acceleration is 3 meters per second squared, and our change in time is 7 seconds. So that's going to give us a velocity final of 32 plus 21. So our velocity final is 53. So on our graph, I'm going to put a 53 meters per second right here. And that will be what our maximum velocity is in this problem. So now to make our graph, our initial velocity is 32 meters per second. And we maintain that speed for 5 seconds. And so that will create a horizontal line on our graph that looks like that. Now for the next 7 seconds, we go from 32 to, which we just calculated, 53 meters per second. So that's going to put us right here on the graph. And so our line's going to look like this. So there's our acceleration. Then it says for the next 18 seconds, we maintain that velocity of 53 meters per second. So we're going to be right here on our graph. And there's another horizontal line, which means we have constant velocity. And then it says that the car accelerates again, but now it accelerates from 53 meters per second for the next 22 seconds down to 0 meters per second. So our graph is going to look like this. And now if we can find the area underneath that graph, we'll know the total displacement. So I'm going to break up my problem a little bit. I'm going to make a rectangle that represents the first 5 seconds. And then we have a trapezoid that represents the next 7 seconds. And I'm going to break that trapezoid up into a triangle and a rectangle. Then we have a big rectangle that represents the part of the problem where we maintained an initial or constant velocity for 18 seconds. And then we have this triangle that explains the whole part of the problem when we're slowing down. So we're going to find the area of those 3 rectangles and 2 triangles, and then we will know the change in displacement. So our first rectangle is 5 seconds wide and 32 meters per second high. So 5 seconds times 32 meters per second will give us 160 meters. For our next rectangle, it's 7 seconds wide and 32 meters per second high. And 7 seconds times 32 meters per second will leave us with 224 meters. For our triangle, we have 7 seconds wide, and then the difference between 32 meters per second and 53 meters per second is 21 meters per second. So we're going to do 1/2 times 7 seconds times 21 meters per second, and that comes out to 73.5 meters. For our big rectangle, when we were going at a constant velocity for 18 seconds, we're going to do 18 seconds times 53 meters per second, and that will give us 954 meters. And finally, for our last triangle, we're going to have 1/2 times the 22 seconds times the 53 meters per second, because that's how tall our triangle is. And seconds times meters per second leaves us with just meters, and that will be 583 meters. So now if we want to know the total displacement, we just add together the total area underneath the curve. So we have change in position equals 160 plus 224 plus 73.5 plus 954 plus 583. When we add those together, our total displacement will be 1,994.5 meters.